Now we come to module 3 of chapter 3. In modules 1 and 2 of chapter 3, we have explained the method of successive approximation to solve Fredholm integral equation of second kind with continuous kernel and forcing term with certain restriction on the parameter lambda. In this module, that is module 3 of chapter 3, we shall explain the method of successive approximation to solve Volterra integral equation of second kind with continuous kernel and continuous forcing function. Consider the Volterra integral equation of second kind given by equation 3.26. Here the forcing function fx and the kernel are continuous in the interval AB and in the square AB cross AB respectively. If we compare the given Volterra integral equation 3.26 with the Fredholm integral equation of second kind as given by phi x equal to fx plus lambda integral a to b kxt phi t dt, we see that the kernel here is equal to 0 for t greater than x. That means in the Volterra integral equation, the limits of integration is from a to x, whereas in Fredholm integral equation it is from a to b, so that kxt is equal to 0 for t greater than x. So we can apply the method of successive approximation to the Volterra integral equation 3.26 as we have applied in the case of Fredholm integral equation. For this, we assume phi naught x, which is the 0th approximation to the solution phi x of the Volterra integral equation, that is equal to phi superscript naught x, and that is equal to fx as given by equation 3.27. We now substitute phi naught t in place of phi t in the integral on the right hand side of equation 3.26 to obtain the first approximation phi 1x of phi x as phi 1x is equal to fx plus lambda into integral a to x kxt phi naught t dt. Now, in view of equation 27, that means phi naught x is equal to fx, which is also equal to phi superscript naught x. So, we find that the first approximation phi 1x can be written as phi superscript naught x plus lambda phi superscript 1x. That is, in this equation fx is phi superscript naught x, and I call this integral as phi superscript 1x, so that we get the equation 3.28, where phi superscript 1x is given by integral a to x kxt phi superscript naught t dt, and that in the operator form is capital K operating on phi superscript naught x. Now we obtain the second approximation phi 2x of phi x by substituting phi 1t in place of phi t in the integral on the right hand side of equation 26, so that we get the second approximation phi 2x as fx plus lambda integral a to x kxt phi 1t dt. Now we know that phi 1t dt is given by equation 3.28. So I substitute phi 1t in this integral, and fx we know that it is equal to phi superscript naught x, so that phi 2x, the second approximation, becomes equal to phi 2x equal to phi superscript naught x plus lambda integral a to x kxt phi superscript naught t plus lambda phi superscript 1t dt, which gives phi 2x, that is the second approximation to phi x, in form of a series containing three terms: phi superscript naught x plus lambda phi superscript 1x plus lambda square phi superscript 2x. Here phi superscript 2x is given by integral a to x kxt phi superscript 1t dt, and that in the operator form is capital K operating over phi superscript 1x. Now if I define phi superscript jx as the integral a to x kxt phi superscript j minus 1 t dt, that in the operator form is capital K operating on phi superscript j minus 1 x, j running from 1 to etc., as given by equation 3.29, then we see that the nth approximation phi nx of the solution phi x of the given Volterra integral equation in form of a series given by phi nx equal to summation I equal to 0 to n lambda to the power I phi superscript ix for any positive integer n. Now I assume that small m is the supremum of small fx, that is the forcing function for x ranging in the interval a to b, and capital M as the supremum of mod kxt, x and t ranging in the intervals a to b, so that we can obtain the estimates of phi superscript jx. Now phi superscript naught x is equal to fx. So fx is always less than equal to m, that is m is the supremum of fx as we have assumed. So estimate of mod phi superscript naught x, it is always less than equal to m. Now come to phi superscript 1x. Phi superscript 1x is given by integral a to x kxt phi superscript naught t dt. Mod of phi superscript 1x is less than equal to integral a to x mod of kxt into mod of phi superscript naught t dt. Now phi superscript naught t dt is less than small m and mod kxt is less than equal to capital M. So that the estimate of phi superscript 1x is less than small m into capital M into x minus a. Similarly, mod of phi superscript 2x is less than equal to small m into capital M square x minus a whole square divided by 2 factorial. In a similar way, mod phi superscript nx is less than equal to small m into capital M to the power n x minus a to the power n divided by n. If I use these estimates in the equation 3.30 in this series, then we get the estimate of nth approximation to the solution phi x of the given integral equation as mod of phi nx is less than equal to small m into summation j equal to 0 to n mod lambda to the power j capital M to the power j into x minus a to the power j divided by j factorial. Now you can see that this series on the right hand side, that is summation j equal to 0 to n mod lambda to the power j capital M to the power j x minus a to the power j by j factorial converges to the function e to the power mod lambda into capital M into x minus a as n tends to infinity, and the convergence is absolute and uniform for all values of lambda. Consequently, the sequence phi nx converges as n tends to infinity to the solution phi x of the given Volterra integral equation for all values of lambda, and hence from equation 3.30 we obtain phi x, that is the solution of the given Volterra integral equation as n tend to infinity, as in form of a Neumann series as given by equation 3.32. You note that for the case of Volterra integral equation, there is no restriction on lambda for convergence of Neumann series, while for the case of Fredholm integral equation, there is a restriction on lambda for convergence of the Neumann series. Now we have seen that how the method of successive approximations can be applied to solve Volterra integral equation of second kind with continuous kernel and the forcing term. Now we shall illustrate this method by considering few examples. We consider example 1. Here we have to solve Volterra integral equation given by phi x equal to f x plus lambda integral a to x e to the power x minus t phi t dt, x lying in the interval a to b. Here phi superscript not x, this is equal to fx, and the kernel kxt is e to the power x minus t. So that phi superscript 1x is given by integral a to x kxt phi superscript not t dt. Substituting the values of kxt and phi superscript not t dt, we get phi superscript 1x as integral a to x e to the power x minus t ft dt, which is written as e to the power x into integral a to x e to the power minus t ft dt. Next, phi superscript 2x is equal to integral a to x kxs phi superscript 1s ds. Here we substitute the value of kxs and phi superscript 1s to obtain phi superscript 2x as e to the power x into double integral a to x and a to s e to the power minus t ft dt ds. Now we interchange the order of integration to obtain phi superscript 2x as e to the power x into integral a to x e to the power minus t ft dt, and the inner integral is from t to x dx. So that phi superscript 2x is given by a to x x minus t e to the power x minus t ft dt. Similarly, phi superscript 3x is equal to integral a to x kxs phi superscript 2s ds. If I substitute the value of kxs and phi superscript 2s, we get the double integral. The outer integral is from a to x and over ds, and the inner integral is from a to s s minus t f e to the power minus t ft dt. If I change the order of integration, then after simplification it finally comes as phi superscript 3x is equal to integral a to x 1 by 2 factorial into x minus t whole square e to the power x minus t ft dt. If I continue in this way, we obtain phi superscript nx as integral a to x x minus t to the power n minus 1 divided by n minus 1 factorial into e to the power x minus t ft dt. Here n runs from 1 to etc. as given by equation 3.33. Now, if I substitute the values of phi superscript nx from equation 3.33 in the Neumann series solution, then we get phi x equal to summation n equal to 0 to infinity lambda to the power n phi superscript nx. In this series, I separate out the term corresponding to n equal to 0 that is phi superscript naught x, which is equal to fx, plus summation n equal to 1 to infinity lambda to the power n phi superscript nx. Substituting the value of phi superscript nx, we get phi x as fx plus lambda integral a to x summation lambda into x minus t whole to the power n minus 1 divided by n minus 1 factorial e to the power x minus t ft dt. Now all the functions are continuous, so the change of summation and integration is possible. Now this series n equal to 1 to infinity lambda into x minus t whole to the power n minus 1 divided by n minus 1 factorial on the right hand side converges to e to the power lambda into x minus t. Substituting this value, we obtain phi x as fx plus lambda into a to x integral e to the power lambda plus 1 x minus t into ft dt, which is the solution of given integral equation valid for all lambda. Next, we come to example 2. Solve the following Volterra integral equation by method of successive approximations. Phi x equal to 1 plus integral 0 to x minus t phi t dt, x lying in the range 0 to 1 as given by equation 3.35. Here the kernel kxt is equal to x minus t and the forcing function is equal to 1 and lambda equal to 1. Thus, phi superscript naught x is equal to the forcing function fx, which is equal to 1, and phi superscript 1x is the integral 0 to x kxt phi superscript naught t dt. If I substitute the value of phi superscript naught t dt here, then we get phi superscript 1 x after simplification as x square by 2. Similarly, phi superscript 2x is equal to 0 to x integral kxt phi superscript 1 t dt, which can be simplified to obtain x to the power 4 by 4, and phi superscript 3x can be simplified to obtain x to the power 6 divided by 6 factorial. So continuing in this way, we see that phi superscript nx is equal to x to the power 2n divided by 2n factorial. Hence, the solution by the method of successive approximation is given by phi x equal to summation n equal to 0 to infinity lambda to the power n phi superscript nx, and if I substitute the value of phi superscript nx as x to the power 2n by 2n factorial, then we obtain phi x as summation n equal to 0 to infinity x to the power 2n divided by 2n factorial, and the series on the right hand side converges to the function cos hyperbolic x. So, phi x equal to cos hyperbolic x is the solution of the given integral equation. Next, we come to example 3. Here, we have to apply the method of successive approximation to solve the integral equation phi x equal to 1 plus integral 0 to x twice t phi t dt, x lying in the range 0 to 1 as given by equation 3.36. Here we see that the kernel kxt is equal to twice t, fx is equal to 1 and lambda is equal to 1, so that phi superscript naught x in this case is equal to 1. Then phi superscript 1x is equal to integral 0 to x kxt phi superscript naught x t dt, so that it comes to integral 0 to x twice t, which gives x square by factorial 1. Similarly, we calculate phi superscript 2 x, that is equal to the integral 0 to x twice t cube dt, and which gives x to the power 4 divided by factorial 2. The third and fourth one, that is phi superscript 3x, in a similar manner is given by x to the power 6 by 3 factorial, and phi superscript 4x is given by x to the power 8 by 4 factorial. If I continue in this way, I get phi superscript nx is equal to x to the power 2n by n factorial. Hence, by the method of successive approximation, the solution of given integral equation is phi x equal to summation n equal to 0 to infinity lambda to the power n phi superscript n x. Here lambda is 1 and phi superscript n x are given by x to the power 2n by n factorial. So if I substitute that, I get phi x equal to summation n equal to 0 to infinity x to the power n by n factorial, and this series converges to e to the power x square. So this is the solution of the given integral equation. So in this module, we have applied the method of successive approximations to obtain the Neumann series solution of Volterra integral equation of second kind with continuous kernel and the forcing function. Unlike the case of Fredholm integral equation, here there is no restriction on lambda for the convergence of Neumann series.